Hi everyone, this webinar is on melting and crystallization, which is part of topic 1. So the first key idea that we're going to look at is that magma and lava, which is molten rock, crystallizes to form igneous rocks. So you do need to know the difference between magma versus lava. So magma, as we know, is molten rock material that contains dissolved gases. It's formed beneath the Earth's surface from the partial melting of rock. As it then rises to the Earth's surface, which is due to density differences, once it reaches the surface, it is called lava. So when magma or lava cool, they crystallize to form igneous rocks. So here we've got, uh, I guess, lava cake. It doesn't have any chocolate on the outside, so it's technically called magma. Then once it breaks the surface, it's then called lava. Okay, so difference between magma and lava. Magma forms beneath the surface. As soon as the magma reaches the surface, its name changes to lava. So you should be able to describe the difference between magma and lava now. Okay, so moving on to the viscosity of magma. This is really important to know because we will be looking at this later in these slides about the importance of viscosity on volcanic landforms and eruptions as well. So viscosity is the ability of something to flow. So if it is non-viscous, it is watery, so it's runny. So water is non-viscous because it's very runny. Whereas honey, treacle, maple syrup is thick and therefore it is termed as viscous. Now, depending on how thick it is will determine whether it has a medium viscosity or a high viscosity. And this does actually as we get an increase in viscosity of magma, we get a decrease in mobility of the lava on the surface of the Earth, and we'll talk about that later in this PowerPoint. So firstly, we can use grain size or texture as a definer when it comes to looking at igneous rocks. So igneous rocks can range from being very coarse grained, such as granite, to be very fine grained, such as basalt. And this is dictated by the rate of cooling. Minerals will grow provided they have the energy to form new bonds. If you cool a rock very quickly, the minerals do not have room to grow, the crystals are small and it's fine grained. If, however, there's lots of energy in the system and the crystals can grow into larger crystals because they can form new bonds, then you get coarse-grained igneous rocks. So if you have a very slow rate of cooling, you'll have a very large grain size, and examples of this include granite and gabbro. So usually it's a very large body of magma that is really deep under the ground. We're talking kilometers here. Now, if you've got a rate that is fairly slow, but kind of in the middle, you usually get a medium-sized grain of or crystallized minerals, and an example of this is dolerite. So this is usually a small body of magma that just forms just below the Earth's surface, and therefore it cools a bit quicker and it has a more medium-grained size. And if you've got a really fast rate of cooling, then the grain size of the rock formed is very fine. It's small, you cannot see it with your naked eye, you have to use a microscope. And examples of that include basalt, rhyolite, and andesite. Now these form above the Earth's surface, so lava from either a volcano or a lava flow. So you should now be able to explain how the rate of cooling determines the grain size of igneous rocks. Now, in terms of the composition of igneous rocks, we have minerals that form commonly in igneous rocks, and you need to know these. So quartz, orthoclase, plagioclase, which are the two types of feldspar, biotite and muscovite, which are micas, hornblende, augite, and olivine are the minerals commonly found in igneous rocks. Now, when we're looking at the two feldspars, orthoclase is pink in color, it has potassium in it and it's found in granites, whereas plagioclase can either contain calcium or sodium, depending on where on the spectrum it is, and is usually white in color. And all igneous rocks tend to contain plagioclase feldspar. So here we've got a picture of quartz, some olivine, and then we've got biotite, some more quartz, and some potassium feldspar. or orthoclase feldspar. So you should now be able to state that the minerals commonly found in igneous rocks are quartz, orthoclase, plagioclase, biotite, muscovite, amphibole, pyroxene, which is your augite, and olivine. Okay, so Bowen's reaction series is really important. This is a diagram that shows you in what temperatures do which minerals first precipitate into crystals out of a melt. So if we have a look at this diagram here, the first silicate minerals to crystallize are olivine and calcium-rich feldspar. Now these create what's called an ultramafic composition. As we move down in temperature, we start to see crystallization of pyroxene and I guess half sodium, half calcium feldspar. And then we start to see amphibole. Now this is our mafic chemical composition. So this is where we get gabbros and our basalts that we see. As we move further down the temperature, we get crystallization of biotite and mica and sodium-rich feldspar. And these form our intermediates, which is our diorite and our andesite. As we go further towards low temperature, the last minerals to crystallize are potassium feldspar, mica, and quartz. And these form our felsic, I guess, composition of igneous rocks. So because quartz has the lowest melting point, it's therefore the last mineral to remain in the molten state. And therefore, similar temperature minerals tend to be found in the same igneous rocks. So you'll always find pyroxene and calcium-rich feldspar in a mafic rock. You'll always find potassium feldspar, muscovite, mica, and quartz in a felsic rock, like granite, for example. So you should be able to state now, with the aid of a diagram, the order in which minerals listed above crystallize from a melt and relate this order to the mineral composition of rocks. Now, we can get formation of metallic ores in a magma chamber. So this is referred to as gravity settling and can occur because of Bowen's reaction series. So as the magma cools, minerals will crystallize. Now remember, it's the minerals with the highest melting point that crystallize first as the magma cools. Now these will precipitate out into crystals and they'll settle to the floor like we can see in our diagram here. If those early formed crystals are of an ore mineral, one or more layers of useful mineral could be formed in a magma chamber. Okay, so we could get more layering here that contains, for example, maybe some copper or some cobalt or something in there that is of, I guess, use to us as humans. Now we can also get hydrothermal deposits as well as a result of magma. So groundwater can be heated by bodies of magma. So if you've got groundwater in the surrounding country rock, that can be heated up. Now this hot water will travel through rocks and it may cause chemical reactions that may break down silicate minerals and dissolve normally insoluble substances. So when we talk about silicate minerals, we're talking about quartz here. Because quartz has the lowest melting point, it's most likely to melt and be dissolved into that hot water. Now, hot water can also dissolve gold, for example, and this is one of the ways that you can find gold as a deposit. Because what happens is this hydrothermal fluid that is rich in silica and gold gets into the fissures and cracks of a rock and it then cools and precipitates the quartz and gold out into minerals. So we get veining of quartz and gold in between joints or fractures in the rock like we see here and here. Now, quartz, which is referred to as a gangue mineral, it's like the waste mineral. We don't want the quartz, we want the gold. It occupies most of the fault and only small amounts of the mineral, in this case gold, are precipitated out. So you can see in this sample here, we've only got a little bit of gold around the edge. Now, New Zealand is a really good example of hydrothermal deposits of gold because they have so much volcanic activity on the island. Groundwater is constantly being heated and then moving around and dissolving minerals into it and then precipitating them out elsewhere. So you should now be able to explain how metallic ores are concentrated by gravity settling and hydrothermal processes. So igneous rocks can be classified according to their mineral composition and their texture. So igneous rocks contain interlocking crystals of silicate minerals. Now, depending on the type of feature will determine the type of group. So if you've got, for example here, rhyolite and granite are light in color, their major minerals are quartz, and they have a very high viscosity. Andesite, which is an intermediate rock, is darker in color, so it's kind of like a medium gray. Its main mineral is plagioclase and it's less viscous. It's not non-viscous, it's somewhere in the middle. And then we've got mafic rocks, which is our basalts, our dolerites, and our gabbros. They are black in color, have olivine and augite as their main minerals, and have a very low viscosity. They're very runny. Now, when we classify igneous rocks referring to texture, this refers to the size and arrangement of grains. So we know that depending on the cooling time, igneous rocks can either be coarse, medium, or fine-grained. Now, the arrangement refers to the presence or absence of layers in the pattern of grains. Now, igneous rocks don't have a pattern, therefore they're comprised of randomly oriented interlocking crystals, and that is a definer when you talk about identifying a rock as igneous. If the crystals are interlocking and they are randomly orientated, it's an igneous rock. If they're not randomly orientated and they have a foliation, then it's a metamorphic rock. Okay, so felsic igneous rocks are your granites and your rhyolites. They both have the same mineral composition but are formed different places on the Earth. So they're both light-colored igneous rocks that have solidified from viscous magma. The only difference is that granite is a coarse-grained igneous rock because it's solidified below the surface of the Earth, whereas rhyolite is fine-grained because it's solidified above the Earth's surface from lava that was extruded by a volcano. So granite and rhyolite are only found on continents and they're never found in ocean basins. They're usually associated with boundaries of continental plates where granitic magma is formed by the melting of rocks deep in the continental crust. Next, we're moving on to intermediate igneous rocks. This is your andesite. It's a fine-grained igneous rock because it's solidified from a fairly viscous lava. It's found on the edges of continents and island arcs. It also cooled on the surface of the Earth, hence the fine-grained. And it's usually associated with converging plates. Now, because it's intermediate in color, because it's a medium gray, it's therefore intermediate in composition. It's neither felsic nor mafic, it's right smack bang in the middle. Okay, moving on to mafic igneous rocks. This is your dolerite, your basalts, and your gabbros. Again, the mineral composition is the same, but the textures are all different, and this is all about the environment in which the igneous rock formed. Gabbro is a coarse-grained rock because it cooled deep in the earth and it had a long time to cool and therefore grew large crystals. Dolerite is a medium-grained rock, intrusive, but it cooled just below the surface of the earth, therefore it has like a medium grain. Basalt is a fine-grained rock because it cooled on the surface of the earth and it's found at divergent plate boundaries or can be produced through volcanism on continents. So here's your gabbro here, coarse-grained, dolerite, your medium-grained, and your basalt, which is your fine-grained. Okay, so batholiths are an example of plutonic intrusions. Now, plutonic means that it is magma that has solidified a long way down in the Earth's crust. We're talking multiple kilometers. Batholiths usually consist of granite and are frequently formed at the boundaries between pairs of continental plates, as I mentioned before when we talked about our different types of rocks. So Granite Island at Victor Harbor, which we went to last term, is part of a batholith that was solidified about 490 million years ago, and it was beneath approximately 10 kilometers of rock and has then been uplifted and eroded away. Okay, sills and dikes are again igneous intrusions, but are what we call hyperbasal, which means they form closer to the surface of the Earth and solidify just below the surface of the Earth. So they're usually non-viscous basaltic magma in composition, and therefore they flow into joints. Felsic magma is really viscous and does not flow as well, which is why you don't ever see sills and dikes made of felsic material. It's only ever mafic material. So sills are formed when magma flows between the layers of sedimentary rock. So we can see here we've got sediments, we've got a sill here, and another one down here, and another sill over here. Whereas dikes are formed when magma cuts across the layers of the contrary rock. And now both sills and dikes are dolerite in composition or classification because they are medium grained, not coarse grained because they cool a lot quicker. So we got a dike here and another one here. So sills may not always be horizontal because the sedimentary layers in which they're intruding may be tilted due to tectonic forces. So we can see here that this isn't exactly horizontal, it's dipping in this direction. And the same with this one, it's dipping roughly in that direction. Okay, so you should now be able to explain the formation of batholiths, dikes, and sills. Now, viscosity of a magma can be determined by three different factors. Temperature plays a role on the viscosity of magma. The hotter, or we should say, I guess, lava, if we're talking about the surface, the hotter the magma or lava, the less viscous it will be. If you have a higher content of silica or quartz, then the lava will be more viscous. So that's why granites tend to be really viscous, is because they have a high silica content in comparison to, say, basalt, and that's due to the chemical composition. All right, moving on to volatiles. These are gases that are dissolved in magma and can include water, carbon dioxide, nitrogen, sulfur dioxide, and hydrogen sulfide. Where you see an increase in volatiles, that means an increase in viscosity. Okay, so viscosity does have an effect on volcanic eruptions. So basaltic lava has very low viscosity, and volcanoes tend to erupt relatively quietly. So this is some footage from the Hawaiian volcanoes in Hawaii. Now Hawaii has basalt that is very non-viscous, it's very runny, and you can see in this video that it does flow relatively easy, and therefore it doesn't really erupt very violently because it doesn't have a lot of volatiles in it. The volatiles do escape, so it is relatively peaceful eruption in comparison to, say, a felsic volcano, which we'll talk about in the next couple of slides. So these are some of the most spectacular pictures of eruptions that I've seen from the Hawaiian volcanoes. And you can see that on the outside it does solidify into a very fine-grained basalt, but it's still molten on the inside. Now this texture here is called ropey, and it forms this kind of what looks basically like rope, and that is typical of basaltic igneous flows. And you can see here again, look how non-viscous, the low viscosity of that lava flows, running not quite as thinly as water, but it is very runny. Okay, so if we have a look at andesitic and rhyolitic lavas, they tend to be very viscous and volatile because the volatiles can't escape as easily. So they tend to have quite explosive eruptions that occur, and fragments can range from being large bombs to fine ash and dust. Now, an andesitic lava, your initial gas pressure is high, but as explosions occur, it starts to settle and flow. So this is another video, and I'll need to skip ahead to, this is Mount Etna from 2011. So this is the head of the lava flow here. And you can see that it is really viscous. It's not flowing like the lava in Hawaii. It's very ashy, and it's very different to the lava that you see in Hawaii, and that's because of the chemical composition. It's felsic in nature, therefore it's more viscous, it has more volatiles in it. It's also a lot hotter as well. So you can see that we've also got bombs coming down the side of Mount Etna as they start to move and dislodge. I mean, look at that huge one there that's just come down. You wouldn't want to get in the way of one of those as it's coming down the mountain range. Now, Mount Etna did erupt recently, I think just a couple of weeks ago, maybe not quite as violently as it is now, but because it is felsic in nature, it is considered to be much more dangerous to be up here filming. So I imagine these are probably geologist professionals that know what to expect when filming a felsic eruption. And you can see that it's just doesn't travel very fast, so it's not going to get you, but because it's got bombs coming off it as well, one of those bombs could hit you as you're running down the side of Mount Etna trying to get out of the way of the eruption. So Mount Etna is andesitic in composition. And again, you can just, if you're just looking at it, it just looks so different from the basaltic lava that you see in Hawaii. It's just, it flows, but it flows very, very, very slowly. Okay, so viscosity can also have an effect on the landforms that a volcanic eruption could form. So basaltic lava, because it has such low viscosity, it can travel long distances and therefore it forms what we call shield cones or shield volcanoes. So this is a shield volcano in Hawaii, and you can see that it's relatively lowly steeping, low sloping sides to the volcano. And the reason why it's called a shield volcano is because it looks like a Hawaiian shield if you were to place it on the ground. Whereas andesitic eruptions like Mount Etna, for example, produce what we call composite cones or stratovolcanoes that are formed by alternating eruptions of ash and lava. And they have much steeper slopes and are more, I guess, what you would consider to be a more typical shape of a volcano. So you should now be able to explain the effect of temperature, silica content, and volatiles on the viscosity of magma and the nature of volcanic eruptions and shapes and sizes of their resulting volcanic landforms. So shield cones, as I said before, is where basaltic magma erupts from a single vent and may form a shield cone. Hawaii is usually a good example of this, and they are basaltic in composition. Composite cones, which was your Mount Etna, your Mount Fuji. These are layers of alternating ash and lava that we can see here in the cross section. And the ash usually includes cinders and other bits of solidified lava as well. And they're usually andesitic in composition. Now, the other type of volcano is cinder cones. Now, cinder cones erupt when rock fragments from Okay, they erupt rock fragments that can be fine volcanic ash to large boulders, and they form when material that was rising from the magma chamber unblocks a vent that was blocked by solidified lava, and then it starts spewing out all this really highly viscous rhyolitic type uh, lava. An example of a cinder cone, because they are quite rare, usually they don't reach the surface, is Mount Schank in Mount Gambier, which is where I'm going to be tomorrow. And I will be going all the way down into the crater of Mount Schank tomorrow when I go up for a bit of a walk. Okay, so the last landform that you can see on the surface of the Earth is flood basalts. Now these result as large quantities of basaltic magma that outpour from a long fissure in the Earth's surface. So unlike a shield volcano, which is from one particular spot, this is from a large crack in the Earth that has spewing out of basaltic lava and covers a large distance. So here we've got one. This is off the coast of, on the east coast of America, and the scale here I've got 400 kilometers, so it's huge. And this one is in India, and you can see that it is massive. It's over 400 kilometers wide, if not 800 kilometers long. So flood basalts are over huge distances. Okay, so you should now be able to explain the formation of the following extrusive igneous landforms: shield volcanoes or cones, composite cones, cinder cones, and flood basalts.